Welcome to the third lecture in Riparian Function and Management. In our last meeting, we discussed course organization, the details on reading material and required books, course structure, grading, and schedule, all which can be found in your syllabus. Also, you saw and heard descriptions of the water cycle and hydrology, precipitation, infiltration, and evaporation, ground and surface water, fluvial morphology, lentic and lotic systems, riffles, runs, pools, and stream order. Let's talk about common language. Common language is essential in building common understanding about riparian function. Also, it is important if we want to communicate with each other. The language we need to communicate about riparian areas is different than the words we use to communicate about dogs or cats or cattle. Some students may be accustomed to using some of the terms in a different way. This could cause communication problems if we do not have the same understanding. Riparian health often depends on a common understanding among people along a shared resource. If you will remember, the understanding and the language of riparian is based on the interaction and the interdependence of soil, water, and vegetation. Some of the basic parts of the riparian area include the channel, which is contained within the stream banks. These are on the soil side of the triangle, but it is hard to talk about channels without introducing the water that it contains. There is the regular flow, which we call base flow. Then there should be a floodplain, a very important component of the riparian area. The floodplain is where flood flows regularly each year. The floodplain is where flood flows regularly reach. The regular flood is one that occurs on average every 1.5 years and spreads out over the floodplain. Creeks and rivers move water and sediment, part of the soil side of the triangle, in balance. This sediment is an important part of the stream. The water table is also a part of the stream, even though it's mostly the waters below the surface and in the banks that are unseen. Finally, vegetation plays a large role in how the stream works and is a part of the stream system. When vegetation dies and is left in place to decay, it is also a part of the system, and this includes large woody material like dead trees, as well as tiny bits of organic matter like pieces of leaves and grass. Because floodplain is such an important factor in understanding riparian areas, we will need a firm understanding of what it is. This definition is from Leopold, 1994. He described it as a level area near a stream channel, constructed by the stream, in the present climate, flooded during moderate and high flow events, should not be confused with terraces or abandoned floodplains, or within the 100-year floodplain. For purpose of this class, when we say floodplain, we will be referring to the place where flows overtop the bank and reach across an average of 1.5 years. This frequency varies across Texas, but for southwest and western Texas, it is understood to be the flood that returns on average every 1.5 to 2 years. Stream channels come in many shapes. Sinuosity is the measure of the channel's crookedness, which depends on the landscape the channel serves. Sinuosity can be measured by calculating channel length divided by valley length. When skiing downhill, the more sinuous the tract, the more gentle and slower the run. Oppositely, steep country generates steeper, straighter channels, and flat country is served by longer, lower gradient streams. Here is how sinuosity or meander works to influence gravity. A straight channel draining a valley that is, let's say, 10,000 feet long, with an elevation drop of about 100 feet, has a slope or a gradient of 1%. But let's say the channel is actually a little bit crooked and is really about 14,000 feet long. The slope or gradient is now calculated at 0.7%. Increasing the sinuosity increases the length, reduces the slope, and results in energy dissipation. It is interesting to note that meander patterns can be spotted even when water flows are not confined by banks. The image on the left, the meander of the Gulf Stream off the east coast of the United States, and a pattern. Water in a channel moves not in a straight line, but in a corkscrew path. The corkscrew eats away at the outer bends. Higher energy water segregates itself from the lower, slower moving water, causing erosion on one side and deposition on the other. Shear stress is greatest on the lower 1/3 of the meander bend. Erosion and deposition are two opposing forces at work in the same stream. Erosion and deposition are balanced when eroded materials are being deposited not far downstream on the opposite bank. A cut bank is where the erosion occurs, and the point bar is where the deposition is expected in a balanced meandering stream. When erosion and deposition are out of balance, eroded materials can begin piling up in the channel instead of being deposited in logical places. We call this aggradation, or the channel can begin to erode excessively, cutting into and degrading its bank and its bed, or eroding laterally, creating overly wide and flat channels. We call this degradation. The opposite is also true. If a channel becomes straight for any reason, it becomes instantly deeper, has higher gradient, and will transport water faster. Channels are still being straightened, mostly to move runoff out of towns and off of fields faster, but that usually does not work for very long, and those downstream of stream straightening projects often experience the negative impacts. Stream channels evolve over time to manage the rate and volume of water, as well as the amount and size of sediment delivered to them. Pictured here is a diagram of channel classification developed by Dave Rosgen. Rosgen has become a popular and influential guru in mechanical and vegetative river restoration. Here's a closer look at the channel classification. Rosgen's system is based mostly on stream and floodplain dimensions. Kenneth Mabin, a stream morphologist and riparian expert, created this approach to considering a stream channel. It is a simplification and a summary of the classification. After all, the reason we look at the channels is to determine if there is a problem. In cutting to the chase, Mabin says, clues to stability or instability, for example, excessive erosion or deposition and degradation or aggradation, typically are revealed by channel dimension or channel shape, by pattern, in your map view that'd be single-threaded or braided, or by profile, which would be the slope. A way to measure and communicate about channel dimension is the width to depth ratio. The width is measured at bank full in the riffle, and the depth is the mean average depth. So width to depth ratio is bank full width divided by bank full depth. The ratio produces a measure of dimension, A healthy functional riparian area aids in keeping the width to depth ratios in good order. In the example pictured above, the width is about 40 feet and the depth is about 5 feet. So the width to depth ratio is 40 to 5 or 8 to 1, which appears to be in keeping with the landscape setting. This channel is able to move its water and sediment efficiently without experiencing excessive erosion or excessive deposition. Like Kenneth Maven said, channel dimension can be a clue to problems with sediment balance. In the example shown here on the upper Nueces River, bankful is hard to determine because the channel is so very overly wide and flat. It was estimated at about 260 feet wide and about 2 feet in depth. So that width to depth ratio could be calculated by dividing 260 feet by 2 feet. The result is a very large number, coming to about 130 to 1. A channel that has reached this dimension will not be able to transport sediment efficiently, and the water quality is going to suffer. Temperatures will be higher, oxygen will be lower. Regional curves for this area predict a width-depth ratio of about 20-40 to 1. Channel formation occurs mostly in the bank-full state. Bank-full flow does most of the work in our streams, moving sediment and forming channels. Occurring on average every 1 to 2 years, the level of flow just before it overtops the channel and spills out into a floodplain. Base flow is the normal amount of water flowing in a stream, sustained by a groundwater discharge and water stored in banks being slowly released. It is not runoff. Last, we have regular flow, which occurs on average every 1.5 years, and is the flow that accesses the floodplain, dropping sediment and building water storing capacity in the riparian area. This level of flow occurs regularly. In addition, there are occasionally very large record flood flows. These record floods are further described by their average calculated frequency, such as 100-year, 500-year, and so on, and by where flood waters reach in each case. Fluid flow within an open channel is measured by finding the average speed water is moving, the height of the water level, and the profile of the stream channel. From this information, a Q, or flow rate, also known as discharge rate, can be calculated. In the U.S., we present the resulting rate in cubic feet per second. When flows are considered within a pipe, as opposed to an open channel, the resulting rate is generally presented in gallons per minute. The U.S. Geological Service operates a series of stream flow gauging stations across each river basin in Texas. While USGS gauging stations do not directly reflect base flow, bank full, and the regular flood flow we have been discussing, they can provide data helpful in calculating these rates for a given stream reach. They can also provide clues to the understanding for riparian health. Pictured here is a hydrograph of the flow rate over New Year's in Del Rio at Rio Grande Village. The discharge measured at midnight on December 31st was just below 600 cubic feet per second. The companion graph here shows gauge height only in real time. Many gauging stations are instrumental to gather data every 15 minutes and are connected to the internet to offer near real-time gauge height and stream flow data. Pictured here is a record of stream gauge height at the Rio Grande Village, showing a gauge height at midnight December 31st, showing 3.85 feet. From the USGS gauging station site, historic data for a given station can also be examined, as well as some of the water quality data. This illustrates peak stream flow. A closer look using the table format for peak flow data shows us that this location regularly experiences high flows of around 10 feet. With this data in mind, an on-the-ground investigation of this location can verify the presence of bankful features and possible floodplain access signs. Some USGS stations, like the Nueces gauge at Laguna, have a continuous record of peak flows going back to 1913. This can be very meaningful data when trying to understand channel evolution and riparian recovery at a given site. Note that the determination of bankful elevation and floodplain location requires an in-depth engineering study. To recap on today's lesson, today we covered the key terms needed to communicate with common language about riparian areas. You will become more and more familiar with these terms as we use them to discuss riparian conditions.